Thank you, Sebastian, for the introduction. I appreciate it. Hello, everyone, and thank you for joining us today. Welcome to our webinar. Today's topic is Fundamentals of Partial Discharge Measurements. My name is Ceren Gürbüz. I'm electrical engineer at Power Diagnostics here, and I'll be your presenter today. I would like to start with just a presentation outline. First, we are going to go into early research on discharge phenomena, followed by occurrence of partial discharges, and then we are going to move into horizontal standard AC 6270, followed by the common PD detector principles. And then properties of electrical PD signals, and in the last two chapters, we will be talking about conventional and unconventional testing methods. So starting with early research on partial discharge phenomena in history, concerning electricity, besides lightning, especially discharge of static electricity amazed mankind and attracted researchers. Here, St. Elmo's fire is a good example, as it led Benjamin Franklin to develop a lightning rod as part of his research and as first described in 1749. Generally, during the 18th century and especially during its second half, many of the basic principles of electricity and magnetism were first subject to in-depth research. In 1762, Johann Carl Wilcke, a Swedish professor, invented a capacitive generator that produces electrostatic charge. And later, Alessandro Volta named this manually operated machine as electrophorus. With this electrostatic generator, the lower dielectric plate was charged using the triboelectric principle. The upper metallic plate with a handle made of insulating material was in use to transfer the charge electrostatically, and however, this caused also charge transfer inside the dielectric plate. Based on Wilcke's work, likewise, in the second half of the 18th century, Georg Christoph Lichtenberg built a large version of the electrophorus and found on the dielectric plate figures formed by initially and accidentally applied dielectric dust. Lacking any photographic possibilities at that time, he transferred the dust figures using a sticky black paper. His electrophorus was very large with a diameter of 2 meters, and it is reported that this electrophorus supported arcs up to 40 centimeters, which corresponds to about 200 kilovolts. He noted already the differences between the traces of positive and negative discharges. Shortly after the beginning of electrification, transmission of electric energy was needed, but as the transmission losses at lower voltage force using large and very costly conductors, the operating voltages of cables were quickly increased. In 1897, John Seely Townsend started his work on the basic partial discharge mechanism, electron avalanche, and which then later became part of his book. So moving into from early researches to partial discharge physics. In a gaseous installation, occurrence of partial discharge simply requires that the critical electric field inception is exceeded and that there is a free ionized electron that can be accelerated in this field. Here, the critical inception field means that this accelerated electron reaches such a high speed and kinetic energy within its free travel path that it causes secondary electrons as soon as it hits another gas molecule. So then the initial accelerated electron causes an electron avalanche. The statistical properties of these processes control the appearance of the partial discharge pattern, and which is very important concerning the identification and interpretation of the PD activities. The initial discharge mechanism, having only the collusion ionization and no space charges involved, is called Townsend discharge. In practical life, the plain Townsend mechanism concerns the so-called tertial discharge, as it occurs initially at sharp points in the negative half cycle. Generally, the Townsend discharge principle applies to small discharge magnitudes up to approximately 10 picocoulombs only. And the figure basically is showing the avalanche discharge like tertial, glow, and corona. Here, the ionization process occurs due to collusions. And this figure initially shows the generation of the additional discharge avalanche due to photoionization. And here, due to radiation, nearby gas molecules are ionized, and they are also causing additional avalanches, which then quickly form a conductive channel, and which is called streamer. And here in parallel, as said, with increased recombination radiation, then the discharge changes into streamer discharge. Here, the ionization process consists of both collusion and photoionization. The next escalation in the gas discharge process is the thermal ionization. In case the temperature in the discharge channel gets high enough so that it causes the thermal ionization, then the number of free electrons increases rapidly, and the current in this comparably narrow channel increases very strongly. So again, with a certain current density in the discharge channel, and additionally thermal ionization then contributes to the generation of free electrons, and the discharge then changes into the leader discharge, covering the stem bunch and spark-like discharges. The leader discharge is regarded as the strongest partial discharge mode just before breakdown. In air, leader discharge can only be maintained in case of a strongly inhomogeneous electric field and with comparably large distances. So now we are coming to provision of starting electrons. Having the critical field to support an electron avalanche, a free electron must be accelerated in this electric field. So fresh polymeric surfaces, such as gas inclusion in a freshly cured epoxy resin or freshly extruded polyethylene, have literally no free electrons. But here, then the electron needed is ionized by the natural radioactivity, which can include the cosmic photons, natural radioactivity of the soil, and radiation due to the radioactive noble gas radon. The sources of this ambient radioactivity cause 2 times 10 to the power 6 free electrons per second and cubic meter. A spherical void of, let's say, 1 millimeter diameter having no own free electrons shows an average statistical delay of 10 to the power 3 seconds to be hit by the first photon. Hence, it takes in average 15 to 16 minutes to be hit by the first photon. And then so that the partial discharge activity of such 1 millimeter void starts. Therefore, this makes clearer the standard testing times. For instance, the common testing type for dry type transformers is around 3 minutes. So it's around 1/5 of this mentioned statistical 15 minutes. So it's too short. So now in the slide, you can see typical breakdown strength of some insulation materials. Paschen's law basically shows the breakdown voltage as a function of pressure and the spark distance, which is also called as free path length. It's an experimental curve, and here shows a near down distance and the long distance breakdown range. Starting with the air, by volume, dry air contains 78% of nitrogen, and nitrogen is rather an electropositive gas, which makes here air a poor insulator, having a breakdown strength of 24 kilovolts per centimeter bar. Other gases, such as hydrogen and SF6, can become a good insulator if used in compressed form, such as in gas-insulated switchgears or gas-insulated lines. And the breakdown strength of SF6 gas with 4 bar at relatively high pressures is about 3 times higher than under 1 bar. So now moving into discharges in spherical gas inclusions, the figure basically shows the initial sequence in such a spherical void in a polymeric material. Firstly, there is the statistical delay time lag until the first energetic photon hits this cavity and then provides the first ionization. As can be seen from this figure, some of the ions and electrons will recombine, while others make it to the adjacent surfaces. And this is in accordance with their derived velocity, of course. And the surface charge here causes an electric field that is superimposed to the external field. And from now on, the internal electric field shows an offset, and that changes with every single discharge event. And upon the reversal of an external electric field, an electron attached to the surface then may be detrapped. And in this case, an electron avalanche occurs in the opposite polarity. But however, this which we call as detrapping mechanism has its own material-related time constant. And also there is statistical variation, since the thermal movement of the trapped electron also superimposes the bond energy, and that means that it modulates the energy needed for detrapping. So visualization of partial discharge activity. I'm talking about the early PD detectors. They were based on disturbance measurement receivers, and many of them were equipped with speakers or even headphones. And this is a picture of one of the early instruments. And this figure is called as an ellipsoid Lissajous, used to indicate the phase position of the PD activity. And here, this graph is showing typical count distribution. And regarding the so-called FQN pattern, which is currently the state of the art, here in each dot corresponds to one single PD event, while X coordinate is giving the phase position and Y coordinate is giving the amplitude of the PD pulse. And the number of the events recorded during the measurement is estimating the color intensity. And the 3D patterns, here you can see on the top, meanwhile provide a different view of the FQN pattern, and it basically does not contain any additional data of the acquired pattern compared to the FQN pattern. So now we are moving into the discharges and spherical gas inclusions. Here, in this case, we assume a high availability of starting electrons. Here you see the applied voltage, which is a sine wave, and then the red lines here are showing the internal electric field. When the critical electric field is reached, there would always be an electron available. And in this case, the internal field breaks down to the residual electric field, here as you can see from the graph, and then the internal field would again increase up to the critical electric field. And this causes consecutive row of pulses of even amplitude. Here on the right-hand side, you can see the regular phase-resolved partial discharge pattern. And additionally, it's very uncommon to have such high availability of starting electron, as well as such a stable magnitudes. In fact, only applying strong irradiation by X-ray or, for instance, UV light having sufficient energy is able to achieve such regular discharges for fresh cavities in polymeric materials. In case there is no such external irradiation, then only ionization processes of the natural radioactivity, as well as the described so-called detrapping mechanism, would provide the free electrons needed to start electron avalanche of the partial discharge event. As the internal surface conductivity of such fresh voids in polymers are in the range of 10 to the power minus 15 Siemens, these surface charges can survive several tens of milliseconds, and they always would remain available for the so-called detrapping mechanism. And the figure is showing in case of a low availability of free electrons to start the electron avalanche. Here the time lag of the electrons derived from natural radioactivity or detrapping is high enough that the internal electric field can become much larger than the critical electric field, which is needed for the partial discharge inception, of course. And here on the right-hand side, the figure is illustrating the typical distributed phase result partial discharge pattern. On the previous slide, we have seen the case with low availability of starting electrons, and here the PD pattern with high availability of electrons is shown. The alternating component of the internal electric field of such cavity is proportional to the applied external voltage, and whereas every discharge activity causes a direct electric field offset, which is here denoted by the Q min. Here we can see the offset. The inception voltage basically is the applied voltage at which partial discharge activity starts, while the extinction voltage is the applied voltage where the activity stops. And the ratio between them is one of the typical indicators for the partial discharge type. And the figure on the left-hand side is showing passes of a single void in epoxy resin. And here, this pattern is showing as it's taken from a void in a polymeric material. Here you can see, compared to the pattern on the left-hand side, lower availability of free electrons. These voids are similar, but they're having different sizes, or the efficiency of coupling to the electron under test is here different due to different amplitudes. And this pattern is from the previous slide indicating symmetrical pattern. And on the right side, here you see an asymmetrical pattern. The symmetrical pattern on the left belongs to an epoxy resin with a single void with average charge generation. However, this asymmetrical pattern on the right-hand side is an example of multiple voids. Here we do have up to 10 gas inclusions, which you can also separate visually on the positive half cycle due to the higher amplitude. And as said, it's relatively easier to distinguish. But nevertheless, on the negative half cycle, the partial discharge pattern shows a higher count rate, while the magnitude is lower. Here, the partial discharge pattern changes into this typical triangular shaped pattern of multiple voids with high availability of electrons. So unlike the previous case, if the gas inclusion is not spherical, but if it is a flat delamination, such as in air-filled pockets between layers of insulating material, then the process to derive the starting electron and to bridge the gap is identical as for the voids. Such embedded air pockets are the consequence of various degradation processes of technical insulation systems, such as delamination within mica layers or gas-filled pockets between layers, paper layers of transformers, or can also be delamination in cable accessories. The figures here show such a delamination in a side view and on a top view. Once the electron avalanche was started due to the first ionization by a photon having a sufficient energy, the discharge is able to bridge the gap. However, this discharge causes a surface discharge on the landing surface, and the radius of the area covered by this so-called Lichtenberg figure on a dielectric surface is proportional to the local electric field at the start of the electron avalanche. So as found with the void discharge process already, the time lag to get starting electron results in a correlation with the local electric field. Also, based on the found linear relation between the electric field and the radius of the resulting surface discharge, the area covered by this discharge is correlated to the square of the electric field. And therefore, the envelope of the partial discharge pattern of an ideal flat delamination is then correlate to the power of 3 to the local electric field. And therefore, here you can also visually see it for voids with low electron availability. It's directly proportional with the electric field. However, as said, for such a delamination, the discharge is has this superimposed curve according to the sine wave to the power of 3, which is more or less like an exponential function. So another typical example is the so-called treeing discharge. Some materials such as polyethylene, propylene, silicon rubber, epoxy resin, and many more are prone to a tree-like growth of a PD channel. And there's always the enhanced field at the tree's tip that forces an ongoing growth. And due to this ongoing carbonization of the older parts of the tree, this activity concerns mostly very small gas-filled tubes in the utmost areas of the tree structure. And for this reason, the partial discharge pattern is in general symmetrical. So in this slide, we see a partial discharge activity, which is more controlled by the strong asymmetry of the electric field. And this is an example of an point plane discharge, and which is a candidate with strong differences to the processes of partial discharge in spherical voids. In case of such a sharp metallic tip, unlimited starting electrons are available. And therefore, due to strongly enhanced electric field at the tip, the critical electric field is firstly reached at the tip in the negative polarity. And here you see basic tertial discharge. And in case the streamer to negative, sorry, here you can see tertial discharge, while on the positive half cycle you see a positive streamer. And when you have such a pattern, here the streamer to leader transition at this sharp tip happens in the positive half cycle, and here the transition into leader is often quite suddenly. And here the incipient breakdown means that the breakdown is beginning to exist or appear like in an initial stage. And with the figure on the right hand side, you still see a tertial discharge, but here the magnitude of the applied voltage is much higher compared to the figure on the left hand side. So discharges of floating potential. This is another discharge activity with metallic surfaces. When we talk about metallic surfaces, we should consider that there are always available starting electrons and immediately. This pattern shows a floating potential, and this is a metallic element in the electric field with typically a small gap to high voltage or ground potential. Here, as soon as the critical field is reached, the electron avalanche can start and the row of pulses of even amplitude are generated. And this setup produces discharge pulses whenever the electric field is changing. And for this reason, the activity starts in zero crossings, but leaves the 90 degrees and 270 degrees area unoccupied. And this is actually very similar to the concept with high electron availability that we have seen in the previous slides. Whereas this pattern on the right-hand side is from a gas-insulated switchgear. Here you can separate each of 3 phases by means of 100-degree phase shift. And here each stripe represents the delay in partial discharge signal. And this is due to the availability of starting electrons at the point where the avalanche starts. And compared to the pattern on the right-hand side, here you have low availability of starting electrons. And this last pattern here on the left-hand side is showing where the floating potential is covered with insulating materials. So here, instead of metallic gap, you have some small insulation particles, let's say. And the discharge magnitude varies due to the time lag of the charge carrier generation, while the small area here of the test voltage peak, this is the maximum, here it remains clear. So looking at all these patterns, it still does not change the general behavior of floating potential. So regarding the influence of high voltage harmonics and its distortions, some basic pattern examples are provided in the slide. Firstly, here you see a pattern from an offline transformer test where there's a core saturation. This is basically a distorted shape of the high voltage with a dominant content of the second harmonic. And this is related to a distortion of the cavity discharge pattern. The larger scattered pattern in the negative half cycle here is directly showing this distortion. And in the positive half cycle with a higher availability of electrons, it is split into two patterns. And here, the second pattern belongs to a generator in a hydraulic pump storage plant. This pattern is basically showing the typical shape of a service-aged epoxy mica insulation system, and also including the cross-coupling of the neighbor phase. And however, the partial discharge pattern here is modulated by the 29th harmonic of the power frequency. And the third pattern here is showing a PD pattern of voids in a polymeric material with a semiconductive interface. The applied voltage here has a content of the third harmonic, and for this reason, it's causing this almost triangular shape of the voltage. Discharges of spherical voids under low rate of charge carrier generation directly reflect the electric field and show the wave shape and its distortions one-to-one. So now in this chapter, we will be talking about evolution of standards, and here our concern is the horizontal standard IEC 6-70. The main objective of the first IEC 270 and its revision 6-70 is the idea of expressing the partial discharge magnitude in terms of charge. It was released in 1968, followed by the second edition in 1981, and followed by the third edition, which is called IEC 6-70 in 2000, and then the version in 2015 is called edition 3.1. Until the revision 2000 in NXC, it is stated in the standard that a detailed treatment of partial discharge measurements on objects with distributed elements in which traveling wave and complex capacitive and inductive coupling phenomena take place is beyond the scope of this standard. And the new revision has just started, and which is called as TC42 MT23. And the related SIGRA documents are TB662 D137, which is the guidelines for partial discharge detection using conventional and unconventional methods, and TB366 D133, and also the IEC 602 478. This is the measurement of partial discharges by electromagnetic and acoustic methods. So with the recent revision of the IEC 6-70 2015, the upper corner frequency F2 is extended to a maximum of 1 megahertz, and a bandwidth is was set between 100 kilohertz and 900 kilohertz. With this addendum, the tightened step voltage requirements for calibrators were introduced. The rise time was set to maximum of 60 nanoseconds, and time to steady state then no longer than 200 nanoseconds. And the stable step voltage duration is to be at least 5 microseconds, and the absolute voltage deviation, delta U, is not larger than 3% of the U0, which is the step voltage magnitude. And here, test circuits for performance tests of calibrators were also introduced, and in the Annex C, you can find the block diagrams of partial discharge measuring instrument principles, and in Annex H, test result evaluation with direct voltage was also introduced. So now we are moving into common PD detector principles. Measurement receivers and their construction pose the main heritage of partial discharge testing, and the early instruments follow the heterodyne principle of such receivers. With the heterodyne principle, the input signal is mixed with the signal of the local oscillator, and the output of the mixer contains both the differential as well as the additive signal. And this figure here is showing the block diagram of a two-stage heterodyne circuit with an input attenuator, the first mixer, local oscillator, the first intermediate, second mixer, second local oscillator, second intermediate, the modulator, and followed by a meter and then oscilloscope. And the figure in this slide is showing the block diagram of an instrument with active integrator with an attenuator and an amplifier, followed by an integrator. Here, peak detector and an evaluation unit, and then ultimately again the meter and an oscilloscope. Here, the evaluation unit has the task to ensure that the behavior is in accordance with the weighing curve of IEC 6270. And here, this block diagram is showing an instrument with direct analog to digital conversion of the input PD pulses with attenuator, analog to digital converter for PD pulses, digital bandpass filter, numerical integrator, AD converter for AC, acquisition unit, and then evaluation and visualization unit. Following the ideas of AC 6270, the so-called quasi-integration using a low-pass filter is sufficient. And therefore, this F2 of the filter block already takes care of the integration. And here the added numerical integrator is obviously not needed. And the next block diagram here in this figure is showing an example of an instrument with integration at a bandpass filter and subsequent analog to digital conversion. It consists of an attenuator. So here again, the PD pulse is fed into an attenuator here and then amplified, passed through a bandpass filter and converted here into a digital signal. Here again, we have the acquisition unit and then evaluation and visualization unit. All electrical methods we mentioned do have in common that they are using bandpass filters to select the frequency band. In this context, the bandpass characteristic of the coupling circuits needs to be considered as well, since this signal contains complex filters of higher order, and their behavior influences the impulse properties of the PD signal. So now in this chapter, we will be talking about properties of electrical PD signals. And to start with, the electron avalanche under dry air atmosphere has a rise time of about 1 nanoseconds. And whereas the rise time for the SF6 gas is less than 200 picoseconds. For this reason, the frequency is up to 400 megahertz, and for the SF6 gas, up to 2 gigahertz are available for partial discharge measurements. However, whenever the test object becomes physically large, the influence of the internal and external leads has to be here considered. And this is concerning the effects such as attenuation, dispersion, and reflection. Likewise, the antenna effects, like here we concern both radiation as well as the reception, including cross-coupling, and the distributed equipment then only reduced a frequency band. So then it's for the we can say for the distributed equipment only very reduced frequency band is then able to reach the PD detector. So we will introduce this with two examples. The first example is a signal transmission in a stator winding of a rotating machine. First, the insulation in the slot section is relatively thin, while the cross-section of the conductor is then comparably large. So the high-frequency behavior here is like a coaxial cable with a very small impedance. Outside of the slot in the core, in the so-called overhang section, the conductor acts like a bare conductor against the remote ground. In the slot section, the impedances are in the range of 10 to 20 ohms, and in the overhang section, it's more than 100 ohms. So here we would expect reflections with each impedance change. And here the corner frequency depends on the slot length, which we will take a closer look in the next slide. The reflection factor that we mentioned is calculated based on the impedances in accordance with the given formula. For typical winding designs, the reflection factor is 80% and can also be more. So above a certain corner frequency, the high frequency components of an impulse-like signal are being trapped within the slot section, and then the signal undergoes a positive reflection at each slot exit, meaning that 80% of the signal will be reflected into the core and then will not be able to reach the coupling unit. And the mentioned corner frequency is calculated based on the formula, which is also a function of the length of the bar. And given the values of the core and overhang length, here with 5 meters, and for the overhang length is 1.5 meters, the relative permittivity of the epoxy mica, here which is 4, and then the corner frequency with this formula is found as 2.86 megahertz. Measuring above this corner frequency is strongly affecting the sensitivity. So here, selecting the proper measurement frequency is main importance. And with example 2 concerns electrical signal transmission in transformers. Whenever the high frequency partial discharge signal travels an unshielded conductor, parts of the signals are radiated. And this is also the case for the previous example as for the overhang of a stator winding. And likewise, nearby overhang coils receive parts of the radiated signal at some point, and this is leading to cross-coupling. In this way, it can be considered that this effect partially compensates the effect for trapping signals because of the mentioned reflections. In large power transformers, there are many unshielded leads of different coils that are being laid and that also meet at different places. And these unshielded leads then act as an antenna for both radiation and reception of the high-frequency partial discharge signals. And this figure is basically showing the tap leads of an untanked auto transformer. Here, the tap lead travel on the low voltage side from each coil to the tape changer. And the screenshot here is showing the frequency spectrum of an acquired signal. While here, the lower graph still shows a spectrum scan, like the previous one, and here the top graph correlates the peak values measured by the spectrum analyzer with their phase positions at a fixed frequency. And this is similar to a PD pattern. However, here we have the microvolt range rather than picocoulombs. And here the figure on the right-hand side is showing the time domain behavior. This helps for comparing the travel time between different terminals. Here the upper trace of the figure shows a signal that travels a cleat bar cable, like here, like these cables. And the initial pulse of the lower trace is caused by the radiated signal. Here at each T point, you have an impedance change, and the signals are then undergoes a reflection. So our next chapter is conventional testing methods. This slide is showing a defect with an insulation material and the possible microscopic and physical effects. These effects can be optical, such as light, or can be mechanical, like pressure waves, or electrical, such as discharge effects, dielectric losses, or high-frequency waves, or chemical effects and heat. The detection methods vary according to the type of the physical effect. In this chapter, we will be talking about IEC 6 to 70 frequency range. So before talking about the testing methods, I would like to start with the IEC 6 to 70 compliance calibration procedure. Partial discharge measurements are relative in terms of charge magnitudes, and they are also not absolute measurements. That means the PD detector is calibrated in the circuit with the test object with a calibrator of known pulse magnitude, of course. And the charge impulse, Q0, is generated by using a step voltage and an injection capacitor, which is C0. And the figure is showing how such a charge impulse calibrator is connected across the test object to simulate an equivalent discharge in the device under test. Of course, it should be avoided to have a straight capacitance like CS here, which is bridging the injection capacitor C0. But with commercially available calibrators, the injection capacitor C0 is typically an integral part of the unit. And looking at the figure, it's obvious that C0 should be small against the capacitance of device under test. Otherwise, the intended charge Q0 is lowered to Q as a function of these mentioned capacitances. And the relevant standard 6 to 70 sets this permissible limit to for C0 should be lower than 0.5 times the capacitance of the device under test. And furthermore, it's very important that the rise time of the step voltage is short, and therefore the amplitude spectrum of the calibration pulse exceeds the bandwidth of the used PD detector. And this graph is showing this requirement. Here, the A represents the bandpass of the measuring system, where B is the amplitude spectrum of the PD pulse, and C here is the amplitude frequency spectrum of the calibration pulse. And clearly F1 is the lower limit frequency and F2 is the upper limit frequency. And with the revision 2000 of the IEC 6 to 70, an alternative method was included in this standard. And in the appendix, it is described that the usage of a digital oscilloscope with numeric integration function to integrate the transient voltage drop UM across a measuring resistor RM of 50 to 200 ohms. And this figure is showing the circuit to calibrate a charge calibrator. Here the resistor RM should be chosen not to produce a ringing of the signal. Also, during the calibration process, the leads must be kept as short as possible. And here you see the voltage drop across this resistor here. In this case, it's 200 ohms. And with the addendum of 2015 of the IEC 6-70, an additional calibration method, which is also called a step voltage response, was introduced. With this addendum, the rise time was set to a maximum of 60 nanoseconds and time to steady state then no longer than 200 nanoseconds, which is TS here. And the stable step voltage duration, TD, then to be at least 5 microseconds. And the absolute voltage deviation, delta U, is not larger than 3% of the U0, and U0 is the step voltage magnitude. It is, of course, possible to perform calibration measurements according to this described method, but in order to issue a traceable calibration certificate, an accreditation according to ISO IEC 17025 is required. And Diagnostix is one of the few companies in Germany which offer a calibration according to German accreditation body, which is also called as the DAX. And the K1A of Diagnostix consists of step voltage generator, which is fulfilling the amendment of IEC 6-70-2015 and has a built-in capacitance that directly gives the charge impulse. And very importantly, it has an injection capacitance, which is lower than 1 picofarad, in the range of 0.8 picofarad, and this value stays constant with every charge value. And the general principle of K1A is keeping the injection capacitance low and fixed with every charge value and increasing the step voltage with the injected charge value, like in this formula. And here you see a general circuit of such conventional IEC compliant partial discharge measurements. Firstly, you have the high voltage transformer, and here you have the quadrupole, which is placed at the earth side of the coupling capacitor. And therefore, the test object can be directly connected between the high voltage supply and the earth. And in practice, it looks like this. Here you have the high voltage transformer. And as a coupling capacitor, you see the CC200B/V of Diagnostix with integrated quadrupole and built-in voltage divider. So it basically senses the partial discharge pulse and sends it as a voltage signal to a preamplifier for conditioning. And this picture on the right-hand side is the PD detector of type ICM compact, together with high voltage control unit of type HV control for manual and automatic operation of the high voltage transformers. For such laboratory measurements, typically the calibrator K1A is used, and as said before, it's calibrated at DAX accredited laboratory of Diagnostix. And this slide concerns the PD detector of type ICM compact, which we have just mentioned in the previous slide. It is the best-selling PD detector for standard measurement tasks during the daily work, for instance, in factories of high voltage components with standard test setups according to IEC 60-70. It provides high modularity and robustness. It comes with a spectrum board offering spectrum display for partial discharge, frequency spectrum analysis, and which is a very helpful tool for noisy environments. Also, the channel multiplexer allows a manual switching between 4 or 12 different PD sources. And besides, it also comes with an optional DSO board for cable fault location. And radio influence voltage measurement function is also available as an option. Now we are coming to unconventional testing methods. Here in this last chapter, we will be talking about acoustic and very high frequency, ultra high frequency measurements. And before we were talking about conventional testing methods within IC range below 1 megahertz, but another way of capturing transient currents is inductive coupling. The most prominent inductive coupling is the radio frequency current transformer. There are different types according to different applications. They can be permanently fixed, or there are also clip-on radio frequency current transformers, which can be seen from these pictures. And the bandwidth of the clip-on RFCT can reach up to 80 megahertz. For the detection of structural sound of partial discharge activity, mainly piezoelectric sensors are used. Here is a figure of an acoustic sensor of type AS75A of Power Diagnostics that comes with a built-in 40 dB preamplifier. The acoustic sensors provided by Power Diagnostics, like in this picture, have a resonant frequency of 75 kilohertz, and they show a bandwidth of about 20 to 140 kilohertz for plus minus 10 dB. Here you also see the acoustic sensor with a sensor fixture of SFX1 on a GIS. It is suited to secure the acoustic sensors on a gas-insulated switch gears. And this is a picture with the fixing magnet and the preamplifier. The magnetic sensor fixtures are for mainly temporary mounting of the sensors on transformer tanks. And the ultra-high frequency range concerns the frequency range between 300 megahertz and 1.8 gigahertz. Here in this slide, you see some ultra-high frequency coupling methods such as external flange sensor, EFS1, and different types of window sensors, and ultra-high frequency wave sensor for power transformers. And here on the bottom right-hand side, you see the frequency converter unit and the input protection unit. External flange sensor is a wideband ultra-high frequency antenna for PD detection on gas-insulated switchgears and gas-insulated lines. And since it's wrapped around the unshielded flange connection, the flange dimensions are required. And regarding external window sensors, they are mainly used to equip older GIS with ultra-high frequency monitoring, and Power Diagnostics offers such window sensors of different sizes to fit the inspection window of the gas-insulated switchgear. And on the bottom right part, you see the input protection unit, IPU2B, and the high frequency converter unit, which is called as FCU2. FCU2 covers the frequency range of 100 megahertz up to 1.8 gigahertz, and therefore mainly used for GIS monitoring. The FCU is designed to withstand the high voltage transients for most applications. However, in some cases, it might be necessary to increase the input protection by means of IPU units. And ultra-high frequency transformer sensors can be used to detect internal partial discharges on power transformers in a frequency range between 300 megahertz and 600 megahertz. And Power Diagnostics provides the valve sensor, which is called as TVS2 for the oil valves. And this slide is giving an overview of the advanced state-of-the-art partial discharge and tan delta measurement tool of Power Diagnostics. The ICM system has the highest modularity and robustness. It provides simultaneous real-time acquisition of up to 10 input channels. It is possible to perform both AC and DC measurements. It also comes with a smart trigger feature for acoustic PD fault location. It also has the option cable fault location. So it is the all-in-one measurement system, including the features of the less complex PD detectors. That means it has a wider application field, such as transformer testing or any user looking for a flexible and modular device that is adaptable on multiple different setups. And of course, it is best suited for researchers and developers. And here we will introduce some useful frequencies for partial discharge measurements. The IC range below 1 megahertz provides the best coverage of the entire test object. But here one might face the issues with noise interferences, and it is regarded as the best choice for conventional offline tests. In general, for post-processing, separating, and displaying of partial discharge pulses, a resolution bandwidth of 1 megahertz is mostly sufficient. For the frequency range between 2 to 20 megahertz, here you still have the reasonable coverage, and this range does also provide the best compromise for online monitoring, and the noise situation in this range is moderate. For 20 to 500 megahertz range, here there is limited coverage of the electrical PD signals, mostly due to the high frequency effects. Because of the signal attenuation, since the high voltage equipment is designed to transmit high currents and high voltages at either 50 or 60 hertz, so not for these high frequency ranges. And the ultra high frequency range is mostly relevant for GIS monitoring. It is still offering a reasonable coverage depending on the number and positioning of the ultra high frequency sensors. Partial discharge signal in a GIS emitting an electromagnetic wave, and then the GIS is behaving as a waveguide here. And the signals therefore are affected from various high frequency effects such as reflection, dispersion, and attenuation, as we mentioned in the previous chapters. Therefore, the sensors must be placed in a way that provides a certain amount of sensitivity. Of course, it is still possible to perform these measurements in the IC range below 1 megahertz, like for conventional methods, but then instead of the sensors, the coupling capacitors would be used. And here, the main problem is that due to on-site online conditions, the background noise is much higher than the acceptable limits. So as said, here in this range, we have comparable low noise interference, and also the ultra high frequency range goes up to here 3 gigahertz, but the frequency converter units are covering up to 1.8 gigahertz, and this is sufficient since it covers the vital frequency components of the PD signal. So here in this slide, you see the overview of our portable products. We already mentioned ICM System and ICM Compact on the previous slides. The AIA Compact is the PD detection and localization device for gas-insulated switchgears or air-insulated switchgears, cable terminations, and transformers, which combines all non-conventional PD measurements such as acoustic, high frequency, and ultra high frequency. The ICM Flex is a measurement system for partial discharge and ton delta, or power factor, as well as capacitance and power frequency. And here it has a unique concept since the acquisition box is under high voltage potential, and this is fully computer controlled, and the communication can be provided via Bluetooth or can also be fiber optic communication. And the ICM Monitor Portable is a compact instrument for evaluating condition of medium and high voltage insulation. It again comprises spectrum analyzer and acoustic detector and a conventional PD monitor in just one instrument. So that was a webinar about fundamentals of partial discharge measurements. I would like to thank everybody for their attention and participating in this presentation. Thank you all very much.
Thank you very much, Ceren. At this time, the presentation portion of the webinar is officially concluded. All right, we'll now take several minutes to answer your questions. So that is a question that comes up a lot. Which equipment is mainly affected by partial discharge? Markus, would you like to answer that?
Yeah, hello. First of all, thank you, Ceren and Sebastian. Yeah, we collected quite a number of questions here today, and we selected a few to get answered. Yeah, as Sebastian mentioned, which equipment mainly is affected by a partial discharge? So, yeah, not easy to answer, but all kinds of electrical equipment where you have high electrical fields can show a partial discharge and internal defects on insulation material. And it's not a question of the voltage level of the asset, it's a question of the internal electrical field strength, which is then causing partial discharge. So classical systems are transformers, power transformer, distribution transformers, rotating machines, motors, cables, GIS, air insulated switchgears, and so on. But today we also find PD in small electric drives, in wind turbine systems, in solar panel foils, for instance, just to name a few. So to answer the questions, yeah, we find partial discharge today in all electrical equipment with high electrical fields. Second questions I see here is whether PD measurement is the best option to detect defects in electrical equipment. So partial discharge measurement, the method is one method to find defects in insulation materials or to find weak areas in insulation materials. But there are also many other defects in electrical equipment that can be found by other methods, for instance, by dielectric measurements using the other Megger instruments available. PD measurement technique has the advantage that it's a non-intrusive measurement method, and it gives a early pre-warning before it comes to a full breakdown of the insulation system. So the PD measurement can furthermore be used for defect identification and also for location, as we do it on power transformer, to get a very clear idea of the root cause and the location of the partial discharge source. Third questions I've noted here is that we should explain again photoionization. That was explained by Ceren quite well, but I will briefly explain it again. So if you have no free electrons in gases, you will not have any PD activity. So to get these free electrons, we need either a material providing these free electrons, or we need ionization. That means a photon from the cosmic radiation hits a local gas molecule and produce then free electrons that which can be accelerated in an electrical field and is then causing the PD pulse. So then the next question on slide 19. Ceren, if you go to slide 19, maybe you will or can answer this question about the difference between high availability of electrons and low availability of electrons, and how that is can be seen on a PRPD pattern.
Thank you for the question. As said, this figure is showing the partial discharge pulse of a single void in an epoxy resin. And here the pattern is clearly showing a higher count rate at the leading edge of the area occupied with pulses. And this indicates a higher availability of starting electrons. And regarding this second pattern, where we said that we have lower amount of starting electrons, here there's this line pattern due to our random statistic ionization processes. So this unfilled part of the pattern is showing that we have lower number of starting electrons, basically.
The next question, what do you mean by photoionization, Markus?
Oh, that's already answered.
It's answered.
The next is about does IEEE exist for PD measurements? That means are there available standards out for partial discharge measurements? Yeah, the answer is yes. There are multiple standards out from IEC and IEEE, including PD measurement methods and procedures for testing high voltage assets, mainly in the factory for quality acceptance test. One example, for instance, is the IEEE C57 for transformer testing. So there are multiple versions out, and yeah, we can maybe share later with our answer to these questions in written form a few examples for typical standards. And you find a list of these standards on our web page under www.pdix.com. So the final question of today, on slide 52, we had, or Ceren, we mentioned that UHF frequency range is mentioned as reasonable or for reasonable coverage, while due to ultra high frequency range, the coverage should be very limited. That's what the author of this question is writing. So here he is saying that, but can be expanded by more number of sensors. Yeah, so the answer is yes, we can expand the coverage by putting more or placing more number of UHF sensors on a transformer or on a GIS. But the general coverage of each individual UHF sensor is very limited, and it's a near field detection. Due to this, we find on a large 400 kV GIS, for instance, multiple sensors per bay, and so in total we can find up a few hundred sensors for a large 400 kV substation, three-phase substation, just to give one example. Okay, so these are the main questions we would like to answer today. Further questions are coming in and will be answered later on in written form. And yeah, thank you from my side for today.
Thank you, Markus. Thank you, Ceren. We would greatly appreciate if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or quote on any Megger products. A copy of the presentation along with a link to the video recording of the webinar will be emailed to everyone in about a week. You can also view video recordings of previous webinars on our website at us.megger.com/webinars. Please register for next month's webinar, Factory Acceptance Test of Power and Distribution Transformers using ICM System. The presenter will be Daniel Hering. It looks like that's all. We apologize if we did not get your questions today, but we will follow up with you offline in the next couple of weeks. Thank you all for attending. Please take some time to answer the survey. The survey also includes a field for you to request a quote or a demo if you're interested. Thank you all again for attending and have a great rest of the week.